All right, today we're talking about something that is literally everywhere, but you've probably never seen it. It's called a quartz crystal oscillator, and yeah, you may not have heard the name, but trust me, your entire world runs on it. So, think about this for a second. Your phone, the internet, your car. What could they possibly have in common? I mean, you've got this tiny computer in your hand, a massive global network, and this complex machine you drive around in. What's the link? Well, the answer is a heartbeat. No, not a biological one. We're talking about an electronic heartbeat. A super, super tiny, perfectly stable pulse that keeps our whole digital world in lockstep. And that hidden heartbeat, that's what this is all about. It comes from this little marvel of engineering, the quartz crystal oscillator. And hey, heartbeat of modern electronics isn't just some catchy phrase we made up. It's the real deal. From the chip inside your laptop to the GPS satellites way up in space, these little guys provide that steady, reliable rhythm that makes everything work together. They are, and I mean this, the absolute unsung heroes of our time. Okay, so how in the world does a tiny piece of rock create a beat that perfect? Well, it all boils down to this really cool physical property. It's almost like scientific magic. It's called piezoelectricity. The Curie brothers, Jacques and Pierre, figured this out way back in 1880, and it is, without a doubt, the secret sauce. Think of it like a two-way street connecting pressure and electricity. So check this out. You squeeze it, you get a little zap of electricity. But it also works the other way. You apply electricity, and the crystal physically bends or vibrates. This back and forth creates this perfect little feedback loop. You zap it, it vibrates. That vibration creates its own voltage, which you can use to keep the vibration going, and bam, you've got this self-sustaining, incredibly stable and predictable pulse. And you can see how this idea evolved over time. It all started with the Curie brothers' discovery in 1880. Then, in 1921, Walter G. Caddy builds the very first oscillator. A few years later, Bell Labs makes a quartz clock that's way more accurate than anything before it. And then the big one for consumers, 1969. Seiko brings out the Astron, the first quartz wristwatch, and boom, it just completely changed the game for timekeeping, making that kind of precision available to pretty much everyone. Okay, now this is where it gets really cool. Not all of these electronic heartbeats are the same, not by a long shot. You know, depending on what you're building, whether it's a simple little gadget or a massive 5G cell tower, you're going to need different levels of precision. So there's this definite hierarchy. Let's break it down with an analogy. A standard crystal oscillator, the EXO, that's kind of like your basic uniform. It does the job. Then you've got the TCXO, the temperature-compensated one. Think of this as a climate-controlled suit, designed to handle temperature swings. But at the very top, you've got the OCXO, the oven-controlled oscillator. This thing is like a full suit of armor, complete with its own built-in heater. It offers just ultimate stability. So let's put some numbers to this. Your standard XO, it can drift by about 30 parts per million. What does that mean? Well, for every million ticks of its clock, it might be off by 30. And for a lot of basic stuff, that's totally fine, no big deal. But then you jump to the TCXO. Just by adding a tiny sensor to watch the temperature and a circuit to correct for it, you get something that's about 30 times more stable. That's a huge leap. And that's exactly why you need them in things like your smartphone or a GPS unit, which have to stay accurate whether it's hot or cold outside. And then there's the top tier, the OCXO. This thing achieves a level of stability that is just mind-boggling. How? It literally puts the crystal inside a tiny, perfectly controlled oven to keep it at its ideal temperature all the time, no drift. This is the kind of insane precision you need for the really heavy-duty stuff, like 5G base stations or sophisticated radar systems. So you might be wondering, how do they even make these things? Well, the process for creating these perfect little heartbeats is every bit as precise as the component itself. I mean, it's really a marvel of manufacturing. First, you have to grow a perfectly flawless synthetic quartz crystal in this high-pressure chamber called an autoclave. Then they use an X-ray to find the absolute perfect angle to slice it into these super thin wafers. After that, it's lapped, polished, and chemically etched down to an exact thickness. That thickness is what actually sets its frequency. Then they deposit these paper-thin metal electrodes on it in a vacuum. And finally, the whole thing gets sealed up tight. And there's a good reason for all that work. As it says here, the performance is profoundly sensitive to its surrounding environment. What that means is even a single microscopic speck of dust or the tiniest bit of moisture can totally throw off its precision. So that last step, sealing it in an airtight case, That's not just packaging, it's a critical shield that protects its integrity. Right, so as our world gets faster, more connected, more data hungry, the pressure on these timing devices is only getting more and more intense. So, what's next? What does the future look like?
Well, if you look at the market right now, the go-to, the main workhorse is something called the AT cut. It's got the lion's share of the market. But what's really interesting is where the growth is. The fastest growing segment is the SC cut. That stands for stress compensated. And these offer even better stability, especially for those high-end OCXOs we talked about. It's a clear signal that the demand for higher and higher precision is not slowing down.
And Quartz isn't the only player on the field anymore. There's another technology, silicon-based MEMS oscillators, and they are a serious contender. They're incredibly tough, like they can survive insane shocks. Plus, they're tiny and super easy to program. But Quartz still has some key advantages. Especially when you look at the top-tier OCXOs, their phase noise is just superior, and they generally use less power. So for engineers, it's a really critical trade-off, a choice between these two powerful technologies. So what it all boils down to is this. The quiet, steady, invisible beat of these tiny crystals is what made our modern world possible. But as we keep pushing for faster networks, smarter devices, and more precise data, the race is on. The race to find an even more perfect heartbeat. And the real question for the future is, what technology is going to provide it?